So here we go. I'm getting the idea that basically we have an upwards tension and downwards weight. And is it being, I don't remember. Is it being accelerated upwards or accelerated downwards? All right, so tension is greater than the weight. We know that the total, let's say net work, is equal to the change in kinetic energy. And we know how much this is because we know the two velocities. So we can calculate that. Not to do the whole problem, there's work done by tension and there's going to be work done by gravity. I'm pretty confident that the work done by gravity is going to be negative because the girder is being pulled upwards. I don't know what the tension is, but I don't think I have to know. Once I know this part and I know all of this, I can just solve for the work done by tension here. Now, once I have that and have the value, I can then say that the work done by tension is going to equal the tension times the displacement. I'm assuming the tension's acting upwards the whole time and the displacement's upwards the whole time. But I'll have to get how much work was done by tension first. And I can get that from this. Is that enough? Or do you need me to do more than that? Okay. That's what I figured, but I want to make sure. All right. Anybody else need a push in the right direction on another question?
Could you start on number 11, which is 9.66?
I probably can. Number 11. Six dogs pull a two-person sled with total mass of whatever that is. The coefficient of friction is that. And the sled accelerates at that. Reaches a cruising speed of that. Okay. So we haven't discussed power. So I would behoove you to wait until after our discussion today and see if afterwards that gives you enough information to figure this out, okay?
Okay, sounds good.
We're going to talk about power today. Anything else? All right. All right, first, I want to show you guys something because, and I did it, unfortunately, I hammered it too hard in fourth period. So I'm going to try and have a little bit of a lighter touch in this class. So I want to show you a problem and from 2010. And just so we understand each other, I would not give this problem to you guys as it stands now because I think you'd just be mad at me. But I want you to see, because this is a fairly contemporary problem and it's been, it's relatively recent. And the problem itself is just mean. So it's not even good for a practice question because of the way the problem is stated. I think that it's just bizarre. Yet this was on the exam, and it's the third problem on the exam that year, which means that after everything else they encountered this problem. So let's take a look at it real quick, because I want to kind of help us understand some of the limits of what we have to do and what's going to happen on a problem like this if you reach those limits. First, the skier is being pulled up the slope with they don't tell you what the force is, but you don't have to because they give you the acceleration. Because of that, they tell us that the magnitude of the acceleration is this function. Now, I think a lot of people will see this function and immediately be very concerned about what they're supposed to do here. But I want to impart that this is just a sine function. And if we look, it has the sine function from 0 to capital T. And if you look inside here, when little t is 0, this whole thing is 0. What is the sine of 0? All right, so the acceleration starts from 0. Now, it's going to go until little t is equal to capital T. When little t is equal to capital T, what is the inside of the parentheses going to be? What is the sign of pi? 0 again. So this function goes from 0 to its maximum back to 0. And that's it. It stops right there because after that, the acceleration is 0 afterwards. Now, first, you might, well, why? Well, why bother with this? I'll tell you, it's real simple. So you don't rip the guy's arms off. That's why. You don't want the acceleration to be all of a sudden, or else you'll hurt him. So this allows for an acceleration that builds and then decays and stops. That's why it's there. And so having accelerations like this are to ensure that, we don't hurt you. It's like, that's why you don't use a spring to launch a person roller coaster. It's fine for toys because you don't break the necks of the toys. But if you put people on a spring launch system, you are applying maximum acceleration at the instant you release the spring, and the acceleration gets smaller over time. Yes, sir? Yeah, except that they don't actually use linear springs for those. And generally, if you're talking like the ones, you're talking like slingshot coasters, or where they pull the ball down and let it go. Which thing are you talking about? Yeah, well, the ball one, you have the luck of fighting against gravity too on the way up. But generally, they use a ever increasing spring so that more of the spring action takes place after you've been released and not at the beginning. So those are done on purpose. But the truth is, in all cases, you want to experience an acceleration, but we want to ease you into it a little bit. Yes, Devon? Actually, the acceleration of cheetah hunt is pretty small, and it's not immediate. It actually builds up so that it doesn't just punch you. It has the current is increased at a rate that is slow enough to keep the initial acceleration low enough not to hurt you. Same thing with like the Hulk or Rock and Roller Coaster. It's a lot of acceleration, but it's never in the extreme. The reason why I'm bringing up a spring is a spring, specifically, we know from our discussion so far, a spring has more force the more you compress it. So with a spring, unfortunately, if you wanted to use a spring to launch you, to have enough energy to get you to the top of that first hill, you'd have to use a particularly powerful spring, which isn't a big deal, except that a spring also delivers 100% of its maximum force the instant you release it. And that force goes down over time as it extends, it gets closer to equilibrium. Well, that's really bad on humans. Our preference is not to be hit that hard at the beginning and then lower it. We would prefer to have it low in the beginning and then increase it. We can tolerate that much better. Luke? The human body, if we're talking about like the human body, that's a very complicated question, because the human body can tolerate certain accelerations along different axes for different lengths of time. So you would have to be more particular. So we've had plenty of humans have endured 50 Gs for very short amounts of time. So like car accidents, it's a lot of acceleration, but not usually for very long. Falling off of like a 4-story building, they survived hitting the ground, but they stopped really fast. So it's a lot of acceleration, but it's only for an instant. Test pilots in the 50s when they were doing rocket sled testing and decelerations, all these people have endured a lot of acceleration, but generally it's not for a very long period of time. So there's the acceleration that could injure you or hurt you if it's applied for a long enough period of time. And that time is different depending on how much acceleration you want to use. Pilots, generally the heart can't pump against 15 Gs. So you can suffocate yourself or provide not provide your brain with oxygen or blood if you can maintain or sustain 15 Gs on the human body for a couple of minutes. But that has to be in a certain axis too. So, all of those things actually play a role in determining you know, the survivability of a high G situation or a high acceleration situation. So is that a thorough enough answer? So I don't know what the number is. So you tend to red out or black out around 9 to 15 Gs though. So 9 you can withstand most people. I mean, the F-16, they developed a special flight suit for them to wear for the high G turns it could perform that would continuously push blood out of the extremities and up into the torso and stuff so they could withstand higher G turns, but it was still all temporary. So they're very thorough. Yeah, I get a very thorough explanation. For more, try Wikipedia. So anyways, it is this first question that bothers me quite a bit. It says, we have this acceleration. So you're going to be accelerated with this action up the incline. Question A says, derive an expression for the velocity of the skier as a function of time during this acceleration. Now, I think that sounds like a pretty tough question, except we should know exactly where to begin this question. And if you don't, well, it's a throwback to the first 2 weeks of school. We have an expression for the acceleration. What do we replace A with? Say it again. How about you people at home? Can you hear what they're saying? Then you should tell me what you think you would replace A with if you wanted to find the velocity.
dv/dt.
There it is. So the first thing you do is you're going to replace that with dv/dt and find an expression for the velocity. But here's the thing. If you wanted to do that, in practice, that sounds fine. But in principle, this is our function, sine, and it's pi over big T times T. I don't think you guys can do it. Based on what fourth period kind of let me know, this might be too far advanced for what you guys can do right now. And perhaps too far advanced for what you'll be able to do by the end of the year. Because right now, can you guys do this integral? Can you take this and find an expression? Now, if you can, fantastic. If you can't, can you get to at least this point? Not enough you were able to say dv/dt just a second ago. And even fewer of you, I think, could get to this point without starting to have some anxiety. And I would expect you to be able to continue, make some decisions. But if you can't get here, you can't solve it at all. Now, you guys who are in BC, you're not there yet, but you had it last year. Many of you who are in AB last year and taking BC this year. So raise your hands again if you're in BC. Keep them up if you were in AB last year. So you should be able to do this. Go ahead, Luke. No. No. That only works if the acceleration is a constant. And in this case, the acceleration isn't. Yes, sir? They asked if you could use a Galilean motion equation, and you can't.
Can you pull out the weights inside the sign? So we just use U sub?
So this particular one, you would have to use U sub. And I know for a lot of you, you haven't done it yet. I expect right now that you can do the left side. I expect that. Because there's nothing there. So all you're doing is taking the integral of 1 times dv, which means finding the antiderivative of 1 with respect to v, which is just v. And then plugging in your limits, which is v and v naught. I expect that you can do that. We've talked about it enough. The right side, I don't think so. And even if I take out the one constant that I have, this is probably right now something that even those of you who have been able to do a little bit of integration will have difficulty with. My AB folks who had AB last year, you should be able to do it. You should be done with it by now. This is a super straightforward one. But I know the reality that this year is different than prior years. Your experiences last year made it so you might not have been able to internalize enough of this information. So for you guys who have never done this before, or you guys who did it but don't remember any of it, I'm not teaching you how to do it right now. I want you to see it because we need to start getting ready for this. We're going to use a process called U-sub. And the reason is because in this particular example, we need to find the antiderivative of sine. Now, at this moment, some of you already know that the antiderivative of sine is minus cosine. And if you don't know that yet, we've even talked about it in class. Stop waiting to learn that. The derivative of sine is cosine. The antiderivative of sine is negative cosine. So get to the point where you have memorized that and just be done with it. But herein lies the problem. This isn't sine. This is sine of another function inside of here, meaning we can do the antiderivative only this. We don't have antiderivative of this with a function inside. So there's a process called U-sub. And U-sub is a method that will help us replace this function with one that is simpler. And we're going to replace it through something called substitution. And it's pretty straightforward in that we simply create a function that, when replaced, will look like a boring old function, right? We want to take everything that's inside here and turn it into one thing, U. Thus, it's called U-sub, because you're substituting U in for your function. Now, although I do not expect you to follow all of the steps here, I'm going to state them anyways. Because the first thing you do is you take the derivative with respect to your variable. So I'm going to take du dt. So this is a constant times t. So I take the derivative, which means the constant stays here. And then I take the exponent above the t, which is just a 1. And then I take 1 away from the exponent, which gives me t to the 1 minus 1. Now I'm going the long way here because I know it's been a long 5 days since you've been at school. And some of you, this is your first return to school in 2 weeks. But this is all just 1. So when I take the derivative of this function with respect to t, I get a constant. Next, solve it for dt. So I solve it for dt. I get t over pi times du. Now, the reason you do all of this is because you're substituting. We're substituting in with u, and we're substituting in for the dt as well, so that I get a new function if U-sub works, then you should be able to, you should be able to get a function that you can then integrate. U-sub doesn't always work, but for almost everything we're going to have, it will. And what I mean is I can take this term and write it out front because it's a constant, and I'm left with a very simple integral. That's how U-sub works. So now I take the derivative. I take the antiderivative. That was not as smooth as I want. Let's see if we can be better. Be better, Mr. Shelton. There we go. I am better. So now I get a max times t over pi, and the antiderivative of sine is minus cosine of u. And I don't want u. I want to replace u with what I did for my original substitution. So now that I'm done, I just put the original substitution back in, which is pi over t times t. And now I evaluate that from 0 to t. That's U-sub. No, I don't expect you to be able to do all of this. In fact, I expect even less, because in a minute, we're going to put in my limits. And the first one is just putting in t, so that's what I have already. The second one is to put in 0. And what is the cosine of 0? So this is the first limit minus the second limit. So now I'm done. I could write it neater, and I should, so that we keep getting a more convenient solution. So V minus V naught equals A max times T over pi times 1 minus cosine pi over T times T. That's the answer. Now, that was all for part A of this problem. You had to get an expression for the velocity, and that's what you had to do. Question B relies on you having the question A correct, as does C and D. I told you it was a really hard question. Now, there are things you should see, like if you put 0 in for T, do you notice that that's going to become 1 minus 1? I think that's important. If you put T in for little t, do you see that that's going to be the cosine of pi? And the cosine of pi is -1. So all of this becomes 2. So at the extreme, it's either a velocity of 0 or a velocity of 2 times all of this. Either way, that's a lot to expect of a student on part A of the FRQ. And then you have to go on to part B, which says derive an expression for the work done by the net force on the skier from rest until terminal speed is reached. Now, that sounds like a lot more work until you realize part B has a word in it. That word makes part B and C and the rest of this problem all relatively easy if you can do part A. Because all that's saying to do is to say, okay, the work done equals, I've got, and I have to put that when I'm at T minus that when I'm at 0. It's really straightforward if you know what you're doing. But what happens if you can't do this math? What do you do in part B or part C or part D? You got all the points for this problem if you stated 1/2 m v squared minus 1/2 m 0 squared. They assumed that if you couldn't do part A, you would be stuck and you couldn't do the rest of the problem. So they gave full credit if you understood that net work meant change in kinetic energy. So although part A was worth like 4 or 5 points, you could still get 9 to 11 points by just using the definition of what net work means. Moreover, I expect you to be able to get to a place like here, which means you could get 2 or 3 of the initial points for part A. You may not be able to do this stuff. You're going to have to come to grips with, if you can't do the mathematics, you can't give up on the FRQ. I told you, you look for words like net. It changes the nature of the problem, makes it easier to solve, and also gives you a starting point. That one word makes a big difference. The next one just wants what the force is to pull them up there at constant speed. All you had to do is put F equals MA, and you got more than half the credit for that problem. So I want to be very clear. Sometimes the math is going to be daunting. It might be daunting right at the very beginning. You're going to have to overcome. All right. Today I want to talk to you about power. And this is going to be relatively brief. Power is a small bullet point, although it's actually quite important in actual engineering. In the AP exam, they make it a relatively small bullet point. So I want to talk to you a little bit about it by definition, and then talk to you a little bit about what my expectations are for problems that involve power. But power is the rate, oops, you should expect better. Power is the rate at which work is done. It's got one of those special words in it, rate. You could also state that it's the rate at which energy is consumed. In cars, we tend to not pay for the work to be done. We pay for how fast the work gets done. That's why cars with more horsepower go faster. It's not that they go to a higher speed necessarily. They just get there faster. They do the work quicker. That's what power is really about. It's how fast can you do work. But don't be confused. High power doesn't mean high force. I want to make sure you understand that from the beginning as just regular people who are going to go out in the world and have to know things. You can buy a motor that's very powerful but can't lift anything. So don't think that you get something that's high powered means it's going to do a job that you want it to do. Power is just how fast it does work. It doesn't tell you how much work it can do, and it doesn't tell you how much force it can apply. Go ahead.
What tells you how much work something can do?
Generally, if you're buying a motor, you look at its torque rating, because the torque rating is how hard it twists, and that's what you're paying for with the motor. So if you know when you're out looking for cars, you don't just look at power, you look at power and torque. So you guys who have like these little four-banger cars that have, you know, they always claim to have a lot of power. They tend to also have a torque range, which means you don't get any of that power to around 5,000, 6,000 RPM. You know, so there's a reason the torque ramp or the torque range is very much RPM dependent. And that's where it tends to develop its power. That's when the turbos tend to start kicking in because you got enough exhaust pressure now to actually use that turbo to blow air into the engine. You know, there's a lot of stuff buying cars. I'm not a car person, but I know a few things. But generally, you're looking for the torque, the torque range or the torque value. So in practice for us, because power is a rate, we write it as a derivative. dW dt. Because it's the rate at which work is done. So being a rate, it is a derivative. Now, we can write it as delta W divided by delta T if we're dealing with a situation where the work is changing at a constant rate. But if you have a function for work, take the derivative with respect to time, you'll get the definition of power. Now, be careful. We're never going to hardly use this, ever. Because our definitions for work tend to be position specific, not time specific. But, and I just have one more thing, just one more thing. If work is done by a constant force, and work is defined as F delta X for a constant force, then if you divide this by delta T, you get force times velocity. So we have two ways of calculating calculating power. It's you divide work by time, or you multiply force times velocity. Those are the two most common ways of calculating power. Work divided by time, or force times velocity. All right. That was real fast. We will definitely not be done with that. So do your best with the homework tonight. I'll see all of you tomorrow. Have a great day. Glad you guys could all be here today. You guys at home, see you tomorrow. Have a great day.